Welcome to Chapter 2, Normed Linear Spaces, the basics. So the plan is to explore in this class linear transformations, linear operators, if you will, on normed linear spaces. So we need to talk norms. Actually, first we're going to talk metrics. Norms will induce a metric. So it is normed linear spaces that we'll be dealing with. But first, just a few little comments about what a metric is in general. And 2.1 is on metric spaces. Metric's a way to measure distance. If we can measure distance, then we can do a bunch of the stuff we do in real analysis. We can talk about open sets, closed sets, compact sets, limits, continuity, boundedness, connectedness, a lot of the stuff you do in regular old real analysis, and you do the same things in the complex setting as well. In fact, the ideas covered in this section are covered and much more thoroughly in the complex analysis 1 class. That's sort of where at ETSU, the material on metric spaces is primarily covered. Might find some reference to this as well in the real analysis sequence, though here the emphasis on metric spaces really appears in the complex setting. Due to a small program, and we can't reproduce it in both, but I may have some notes out there in both of those settings. Okay, so to define a metric on a set, of course, you're familiar with metrics. Absolute value is a metric on the real numbers. It's a way of measuring distance. You measure distance using absolute values. Absolute value of the difference of two numbers is the distance between them. And you're used to the distance formula from R2, the Cartesian plane. But here we're defining it on an arbitrary set. These other things will yield some examples of metrics, but the input is elements of a set. Actually ordered pairs of elements of a set. So we'll take set X, Cartesian product with itself. So the input will be pairs of elements of set X. The output will be non-negative real numbers. So we're allowing a distance of 0. There's no negative distances, and any positive real numbers also allowed to be a distance. And we require the following. For all X, Y, a little typo there, X, Y, and Z, points in set X, we require the triangle inequality. The distance from X to Y is less than or equal to the distance from X to Z plus the distance from Z to Y. In some very crude sense, the shortest distance is directly between X and Y. I want to say along a straight line, and I can if I've got the right setting. But I'm really stretching our setting here to say something like that. But think of the triangle inequality as it's quicker just to go directly from X to Y than it is to go from X through some third point Z and then go to Y. Could have equality in R2 if Z was collinear with X and Y and between X and Y. But the usual triangle inequality, you're used to that from sophomore linear algebra and all over the place from the analysis classes. Symmetry, the distance from X to Y equals the distance from Y to X. Very intuitive thing we should have. And finally, the distance from X to Y is 0 if and only if X and Y are the same point in set X. D, satisfying these conditions, is a metric. And set X with such a function is called a metric space. That's what a metric space is. You're familiar with these from analysis. Take the real numbers and specifically take the metric to be d of X comma Y is the absolute value of the difference, the absolute value of X minus Y. That's a metric. You know that's a metric. You use that in one-dimensional analysis all the time. And of these properties establishing we have a metric, of course, usually the tricky one is the triangle inequality. In Rn, a metric, there's multiple metrics out there, but one metric is given by taking n tuples. Rn will treat as n tuples of real numbers. It's just a set. I don't necessarily have any algebraic structure in this conversation. In Rn you do because you can add vectors together. You can't add points together. You can add vectors together. Let's interpret it simply as a set of n tuples of real numbers. And we'll define the distance from this n tuple to that n tuple to be the sum of the absolute value of x sub n minus y sub n squared. Sum those up from k equals 1 to n, and then take a square root. A little typo. Should have subscripts of k there. So we're taking differences of corresponding entries, corresponding coordinates, if you like, if I treat these as points, squaring that and summing up. Of course, the absolute value is not necessary. I kind of like that. I got my reasons for putting the absolute values in there. Not so much for the real setting, but if we were to try to mimic this in the complex setting, we'd want that absolute value, that modulus sitting there. But this is a usual, sometimes called a Euclidean metric, the Euclidean metric on Rn. Okay, just a handful of definitions and some commentary. As I mentioned, it's a pretty short section. Take set A in a metric space, x comma d, and a point x. We're defining the distance from point x to set A as the distance from x to A is the infimum of the distance from x to lowercase a as lowercase a ranges over set A. That should have some geometric meaning to you. Have to take an infimum because there might not be a minimum. We can get some odd behaviors because using an infimum to define this, it's a little early for this conversation, but we're effectively using a limit. So we can get odd things to happen, like the distance from x to a can be 0, and yet x not be in a, but must be awfully close to a if that's the case. Take x to be the point 0 and a to be the set 0 to 1, open interval from 0 to 1 in the real numbers. And those are disjoint, or I should say the set A doesn't contain element x, yet the distance is still 0. That distance isn't attained if I take any x, take x equals 0 and any a in this interval from 0 to 1, the distance between them will not equal 0, but the infimum will. Sequences. If we've got metrics, we can define limits of sequences. A sequence, x sub n, in a metric space, x comma d, converges to a point x in that point set if, so the logic starts here, same definition you have in calculus 2, except we're measuring distances with a metric instead of absolute value. A natural number such that when index lowercase n is greater than or equal to capital N, we have the distance from x to x sub n a little less than epsilon. More of that in a second. X is called the limit of the sequence, and we'll write this as x equals the limit of x sub n. Maybe the limit as n approaches infinity of x sub n, or simply as x sub n approaches x. A little comment. This is the same thing you had in calculus 2 when you talked about convergence of sequences, except you'd have an absolute value of x minus x sub n here, but that's the metric on the real numbers, absolute value of difference. This being a graduate class, the following commentary hopefully is not necessary, but I'm going to go through it anyhow. Don't think the limit means something like closer and closer, but never gets there, because that ain't what it says. For all I know, it could get there. A bunch of these x sub n's could equal x, and that distance could be 0. They could get there. And there's nothing about closer and close. If you want an informal way of talking about, say, limit of a sequence like this, if anything, it involves getting close and staying close. And an arbitrarily close as well. Somewhere in there, there's a for all epsilon greater than 0. But there's nothing about closer and closer, but never gets there. It could get there. Also, it doesn't say it gets closer and closer. The x sub n's get close to x and stay close to x. Eventually, you give me epsilon first. That's how it's the way the game is played. You give me epsilon first, and then I can find you a capital N such that eventually the x sub n's are within epsilon of x, and they stay that close. So for any given epsilon, eventually x sub n and x are within distance epsilon of each other, and they stay that way. That is, for all values of the index greater than or equal to capital N, this inequality still holds. They eventually get close, and there's your eventually, whatever capital N is, and they stay close. For all indices greater than or equal to capital N, the distance remains less than epsilon. So just a quick commentary about what limits really are and some common misconceptions that arise sometimes in calculus. We can talk continuity as promised. You give me a metric, I can do all sorts of stuff. We could talk open and closed sets. We don't quite do that here, but we certainly could, and we will soon. Let x1 d1 and x2 d2 be metric spaces. So we got 2 point sets, and a function mapping x1 to x2 is continuous at point P, an element of x1, if. So the logic starts here. And even this is about a gets close and stays close. It's a little more complicated in the function setting than it is in the sequence setting. I've got to deal with input and output values. There's a reason there's these two things. There's the epsilon and the delta, the epsilon for the y values and the delta for the x values. But we're measuring distances differently in the two metric spaces. One of them uses metric d sub 1 and the other one uses metric d sub 2. So this is going to be pretty much the same definition of limit you see in calculus 1. But in calculus 1, you measured distances with absolute values in both places because it was all real numbers there. Here, we'll have a distance measured with d sub 1 and a distance measured with d sub 2, two metrics here. In the real setting in calculus 1, both of those metrics are absolute value. But picking back up with the logic, for all epsilon greater than 0, there exists the delta greater than 0, such that I can read this as if then, if you like, the distance from P to Q less than delta implies the distance from f of P to f of Q less than epsilon. All right, we fixed point P to start with. It comes from x sub 1. Think of it as that's a fixed point. Q is a point within delta of P. And both of these are points in x1. So we measure them with metric d sub 1. So provided the distance from P to Q is less than delta, then the distance from f of P to f of Q is less than epsilon. Standard definition of continuity, except input values that come from x sub 1 are measured with metric d sub 1. Output values that come from the function are elements of x sub 2 and measured with metric d sub 2. Other than that, that's your standard epsilon delta definition of limit of a function from calculus 1. These two ideas we've developed kind of interact. Theorem 2.1.a, the proof of which is kind of left as an exercise, says a function f mapping metric space x1 to metric space x2, is understood to be the setting, is continuous at point P and x1 if and only if, for each sequence x sub n, a subset of x sub 1, capital X sub 1, with x sub n converging to P, we have the limit of the function values, f of x sub n, converging to f of P. We could have, since it's an if and only if result, we could have defined continuity in terms of this instead of the definition we had. But this is a standard layout of the ideas and the relationships between them. I like the way we've done it because it's so calculus. This is all just calculus, calculus 2 probably, and this is just calculus 1. And the relationship between the two, possibly this result. Possibly you don't see in calculus. You'd certainly see it in senior level analysis, though. And a final definition. Let Xt be a metric space and A a subset of X. So it's a set of points from set X. The diameter of A is defined to be the supremum of the distance from X and Y, such that X and Y are in set A. So what you're doing for the diameter of a set is seeing how far apart the points in that set can be in a limiting sense because it's a soup. Set A is bounded if the diameter is finite because we've defined diameter in terms of a soup. It's effectively a limit and it can be infinity. So the diameter of a set can be infinite. Take the whole real line, the real numbers, under the usual metric, of course, that has infinite diameter. This might sound a little familiar to you if you've got some exposure to graph theory. That's the same way you define the diameter of a graph in graph theory. Notice the similarity, the definition of diameter of a set and a diameter of a graph. Got a link there specifically to that. Now things are a little less complicated in graph theory because there's none of this supremum stuff. There'd be a maximum. We're dealing with something discrete, something finite. So there's no suprema. A maxima are achieved in those settings. But still for a graph, you define a way to measure distance, you define a metric on a graph, and then you define the diameter of the graph as the maximum distance between vertices, two vertices of that graph. So it's quite similar to what we're doing here. So there's a quick little intro to metric spaces. We'll look at norms in the next section in 1.2, and the norms will induce a metric. Provided we can show the alleged metric satisfies the three parts of the definition, then we're good to go. But we'll use norms primarily from here on out to measure distances. That means they're inducing a metric, the metric induced by the norm. We'll be dealing with normed linear spaces throughout. Sometimes the norm will be induced by an inner product, maybe dot product to you from linear algebra. Sometimes not. Sometimes we'll have spaces that have norms determined by inner products, dot products, and sometimes not. So we'll see specific examples of that. But on to norms in section 1.2. I'll see you there. Bye-bye.